Hi, my name is Chelsea Scott, and in this video, I'm going to be discussing why we can use remote sensing to measure change from natural hazards. And this video is going to be part of the Open Forest 4D project funded by the U.S. National Science Foundation. So before I really motivate remote sensing, I'd like you to pause this video for a little bit and think about a change that you've noticed in the natural landscape or the other places around you. When did you notice this change? And how has this change affected the area or the people, plants, and animals who live there? Take a little bit of time and think about that. All right, now I'm going to show you a couple examples of change in Arizona. So here we're looking in Tempe, Arizona, and this is in downtown Tempe, and this is a Google Street View image from May 2011. And we're actually here, looking near the Tempe Transportation Center, and we see that there's no building here in the foreground of the image. And then we can time travel, and here we are 11 years later, and we have this new hotel here. And so here's an example of change going from no hotel, so this empty space, to this hotel. It's change in downtown Tempe. And we can think about how this impacted the area. So it's a new hotel, so that's going to be an important place for different visitors in Tempe to stay. We can look at the cars and the Tempe Transportation Center to understand how people move in this area. And if you're on the north side of this building, you also have new shade provided by this building. And here's another example of change. This is looking at the microburst in Phoenix and Tempe in October 2025. And in particular, here we're going to be looking at the Desert Botanical Gardens. So here we see a beautiful Palo Verde tree with its yellow leaves. This is before the microburst. Here is that same area, and now it's after the microburst. And this Palo Verde tree is no longer here. And in fact, it was blown down by the heavy winds during the microburst storm. And we can look elsewhere to get a sense of the processes involved in blowing that tree over. So this is another Palo Verde tree at Arizona State University that we see that it's fallen over, but it's still there. And with it, it brought up this soil and created this mound of soil along its roots. And so this, last image gives us a sense of that intervening process of what the fallen down tree looks like before it was removed. So why use remote sensing to measure change? So first, what is remote sensing? So remote sensing is a set of observations that we can make at a distance. And in particular, of these examples looking at the Earth. So this example here at the Desert Botanical Gardens, and then this one here in downtown Tempe, these are all photographs. And so this counts as remote sensing, where we're making these observations of what the area looks like. We can then compare them over time to see how the Earth has changed. But we can also use remote sensing taken by using images taken by airplanes or satellites to get bigger scale pictures of change. So I'd like to motivate two reasons for doing this. One is that particularly, with airborne or satellite data, we can see features at a big scale. And so here is an image that I took from an airplane that just taken off from the airport in Phoenix. And we can see the suburban development here, the natural areas in the mountains. And with images like this, we can learn about how people live in the area and the interaction between the human and the natural environment. And I always like to joke that you can see who is a geologist on an airplane because they want the window seat. And I quite like to sit in the window seat and just see the different areas, see what they look like from really that bird's eye perspective. And with this perspective that we get from airborne and satellite data, that's very helpful for not missing the forest for the trees. And so if we're looking at wildfires, there's some questions that we can look at, particularly with this bigger scale. For example, can ask how big was the wildfire and what was the full extent of where it occurred? And really that big scale imagery and other data sets make these sort of measurements much easier. We can look at how did the fire change the vegetation and tree cover across the landscape, so not just in a handful of local areas. We can then look at other hazards caused by the wildfire, such as has the wildfire increased the chance of erosion or debris flows. We can look at questions of long-term health, such as how did the wildfire impact the natural landscape, human health, and safety. And the other real reason to use remote sensing is it provides, it's essentially a time machine. So with remote sensing data, specifically imagery, we can see how the landscape looks across decades. So we saw the before and after, for example, for that tree in the Desert Botanical Gardens. And then in downtown Tempe, I showed you the Google Street View from 11 years apart. So with remote sensing data acquired at different times, we really can see what the landscape looks like and how it changes over the decadal time scale. And importantly, we can reuse older data and ask new questions and apply modern data analysis and computational techniques that weren't available when the data sets were originally acquired. And so here's an example, another example looking at change in Tempe, Arizona. And these are images available from Google Earth in 1985, 1997, and 2023. And we're looking at this freeway interchange, which in 2023 is very well developed and is heavily used. In 1997, you can see actually the road was being developed. For example, here, this part of the road does not go anywhere. And also see here that the image is black and white. And so we had lower quality remote sensing data available. And we can go back in time even further. This is in 1985. And here we see that there is a road here, but it is not yet being developed into a freeway. And while we can see features in this image, the image is quite blurry, and really we can't see the detail that we can see in either of the two later sets of images. One of the data types that I use the most is called lidar, and this stands for light detection and ranging. And here's showing you an image of airborne lidar. So here we have an airplane that is emitting laser pulses, mostly in near infrared, sometimes in green light. And the airplane will send out these signals, and they will then bounce back off different features at the ground surface. For example, trees, houses, and the bare earth ground. And we can then use this information to calculate the elevation of the bare earth surface, as well as different features on the ground, such as trees and buildings, and build a really high resolution map of elevation. And high resolution is going to be at least one measurement, often many more, per square meter. And so here's an example of a lidar point cloud. And so this is actually at the Desert Botanical Gardens. And here, each of these colors is actually a 3D point that represents one of the returns to the lidar sensor. And this is colored by elevation. And so the reds are going to be trees. Those are going to be the highest elevation features in the area. These rectangular features are buildings. And then the lowest elevation areas are the bare earth ground, and they're going to be in this blue to green color. And we can also represent LiDAR data in 2 dimensions shown here. So this is looking in New Zealand, and this is showing a topographic hillshade or shaded relief map. And in particular here where it's rough, that's where the forest is. And the roughness is created by subtle variations in the elevation of the top of the tree canopy. And then this smoother area here, these are the agricultural fields where the elevation varies more smoothly. And we can also see some drainages or small creeks here that do have some roughness, and that is the vegetation. So thank you for watching, and this concludes this video.